All right, terrific. Thank you very much, Mario. It's certainly my pleasure to be able to talk to you about some of these things. I really appreciate everyone who's here and joining online. Glad that we're able to make this conference work so remotely. And a special acknowledgement to those of you who are on the west coast of the Americas or even farther west for some heroic efforts to be awake very early in the morning. As you might expect, since I'm at Space Telescope Science Institute, or STSCI, I will be talking quite a bit about the James Webb Space Telescope, JWST or Webb, because STSCI is the Science Operations Center for this observatory, as well as the Mission Operations Center. Although for many of us trying to do our science, it's that Science Operations Center piece that gives us the strong connection. But I do want to start here. This is a bit of community artwork. There's a hashtag JWSTArt that a number of different people have been contributing to. So I like it not only for the beauty of the image with the representation of the JWST segmented mirror up here, but also we have a hint towards ground-based observations. And that's actually a point that I will return to while focusing on these thermal infrared opportunities. To point out that while there are some obvious advantages of going to space, there also remain advantages on the ground, and that we're best off for advancing our science by keeping these complementary. So on to JWST. A little bit of a reminder, I hope, for most of you that this is a 6.5 meter segmented telescope. It will be going to L2, so 1 million miles away, 1.5 million kilometers away. NASA is the lead space agency for this mission, and there's also strong support from the European Space Agency and the Canadian Space Agency. This is a major effort, and it really does take all of those organizations. The bottom line that you may all be very interested in knowing is that right now we are on track for a launch at the end of October of next year. So just over a year away till our expected launch. We as scientists will have to be patient for a little while after that because there's a 6-month commissioning period. And so after launch, we really won't begin science observations for another 6 months. But we will be learning a lot about the telescope and the instruments and their performance over that time. To give you a little bit of a sense of the reality here, this video was very recently released by NASA as JWST has just completed its environmental testing. So the whole observatory is together. The telescope mirror, the instruments, the spacecraft, and the all-important Sunshield. And these environmental tests included vibration and acoustic testing. And all of that was just completed within about the last week, and it went very successfully. So that's a good important point for us all moving forward. What's coming up next is a number of deployment tests, and this Sunshield deployment will be one of the more challenging. The 5-layer Sunshield, which protects from the heat of the sun, is very important. It's also one of the more challenging aspects of the whole observatory, and it is particularly challenging to try to test on Earth in the gravity environment. While simulating the environment of space. So that whole process of the deployment tests will be occurring over several months coming up. And so it'll be a while before we have some more definite news of how that goes. As you might expect, JWST has a really broad range of applicability. We describe it in terms of 4 science themes: first light and reionization of the universe, assembly of galaxies, which really covers all of the development and evolution of galaxies, a birth of stars and protoplanetary systems, as well as planets and the origins of life. As you can imagine, that really winds up encompassing the full range of astrophysics that any of us may be interested in. There are 4 different instruments, each of which have multiple modes of use. So probably for your science case, there is a way to use JWST for it. And some of the challenge is to identify what the best approach is to that. I'll start here with the mid-infrared instrument, or Miri, because that's the one that's probably most obviously resonating with us thinking about thermal infrared opportunities. So the waveband covered is from about 5 to just over 28 microns. And these multiple modes include not only imaging and straightforward spectroscopy, but also an integral field unit, as well as a coronagraphs. And so what we're looking at here in the image on the right-hand side is a Miri simulation with that IFU. And so what we can see here is getting not only the reconstructed image, but also through any particular region, being able to extract the spectrum of that distinct source. I do also want to point out, though, that while the other instruments have near-infrared names, they actually are very applicable for us. That all of them cover out to 5 microns or longer in terms of their capabilities. So what we're looking at here are a few different examples. In this case, on the top left, what we're looking at with the near-infrared camera is just the footprint of the 2 different modules, being able to cover a relatively large area on the sky. What we're looking at on the top right is slitless spectroscopy with the instrument called NearInfrared. And so in this case, this is a simulation of a cluster of galaxies. And so in the slitless spectroscopy, there's the risk of the spectra overlapping. And so by observing in 2 orthogonal directions, it's possible to reconstruct the spectra. On the bottom left here, we've got an example from NearSpec, which is actually a calibration observation. And this is of one of the exciting modes that NearSpec brings, which is to provide multi-object spectroscopy, as well as that 4th example from Miri that I had shown before. So we've got these 4 instruments, all of which are really bringing lots of different modes. So as I said, for thermal infrared, consider all of the instruments depending on your science case, which are providing additional coverage for imaging, spectroscopy, as well as a near-infrared IFU mode. The opportunity for multi-object spectroscopy, slitless spectroscopy, some specialized time series modes, which are particularly useful for some exoplanet atmospheric observations, as well as an aperture masking interferometry mode. So rather than try to discuss all of that in the abstract, one way to be concrete about it is to look at some of the particular science cases, those that have come out of the Director's Discretionary Early Release Science Opportunity. And so this was a community opportunity open for peer review of new programs to be conducted early. And as a result, there are 13 approved programs across all science areas and using most of the key instrument modes. So the selected programs have more than 250 investigators, plus at least 400 additional collaborators. And in fact, I suspect that many of the people who are on the line are some of those investigators and collaborators in these programs. That was some of the motivation to bring in the broad community. It's actually very helpful to have these large teams. About 500 hours of director's discretionary time was made available for these observations. And the intention is to try to conduct these observations soon after commissioning. We hope within a period of about 3 to 5 months once science observations begin. And one important point for all of us is that there's no exclusive access or so-called proprietary period for any of these data. That was part of the intention, to be able to make the data available for everyone to learn about JWST and learn about how to work with the data. Something of interest for US investigators is that the observations from these programs are open to archival research in Cycle 1, relevant for US investigators who are eligible for some funding support, but for everyone, just doing the science with the data is possible. One further point about this program that's pretty exciting is that these science teams are responsible to deliver science-enabling products. So not just to do their own science and not just to make the raw data available. So many of the teams have plans for particular software for analysis, as well as reduced data, or doing some work leading workshops to help people understand how to use JWST. So I've got just a few examples here of some of these DDERS programs. The first one here, Cosmic Evolution Early Release Science, or SEERS. These are observations that will be done in the extended growth strip, providing images and spectroscopy over the field. And one of the exciting things that will come out of this is the expectation for a relatively large number of very high redshift galaxies. Something like 5 to 50 galaxies at redshift greater than 10 is expected. So it's a mix of different kinds of observations, different modes, including the spectroscopy as well as the imaging. And so these are some simulations to give an idea of some of the expectations for what we'll be able to get with JWST. So here we're looking at a Spitzer-Irac image of a relatively nearby Z2 galaxy. And then this is a simulation of what's to be expected with NIRCam. So really a lot more detail to look at the morphology and to use some of the different color information to better understand this galaxy. On the right, we've got a different example looking in the candles field where we've got multiple sources and compared with the previous observations that couldn't disentangle them. Looking with Miri, we not only identify the different objects, but are able to tell some of their differences. And down below, we've got a specific example of a redshift 6 L-star galaxy, where there are a number of diagnostic emission lines to tell us, for example, about the ionization parameter or even the metallicity of the galaxy. This next one is an example that's very near and dear to my own heart. This is looking at the Starburst AGN Connection in merging luminous infrared galaxies. And so there are 4 distinct, relatively nearby galaxies that will be observed with this program. Using NearSpect and Miri for IFU spectroscopy, really getting that spatially resolved spectroscopy over the full range from about 1.5 to 29 microns within the field of those IFUs, as well as providing several distinct images. And so what we're looking at here on the right is a Spitzer spectrum that identifies some of the features that will come through in the spectroscopy, looking, for example, at the silicates, the ionization lines, as well as some of the polycyclic aromatic hydrocarbons. But a really exciting thing using these IFUs is to be able to spatially as well as spectrally distinguish these different emission modes. And then finally, one more example out of the DDERS programs is high contrast imaging of exoplanets and exoplanetary systems with JWST. And so one of the science goals here is to observe exoplanets over the full wavelength range at which they emit. And what we see here on the left-hand side is an example of why that's useful. The different colored lines are different models for exoplanet atmospheres. And so at the shorter wavelengths, there's not a lot of distinction between them. There really isn't a lot of diagnostic power in those observations. But as we get into the thermal infrared, there are real differences among the models. And so by making those observations, the team will tell the difference between them. A second science application here is to use an example case of what a survey for planets at relatively large separation might look like. And so here we're plotting the separation and the contrast of planets These lines through here are showing the sensitivity of JWST. And these bars across here are a number of different models around a solar type star. And so some of what we'll be able to get with this is Saturn and Neptune analogs at relatively large separations, those will be distinguished. So this program is looking at a few different sources using different techniques: coronagraphy, direct spectroscopy, as well as aperture masking interferometry. So I said we're on track for the schedule, and that includes a piece of the schedule that's for us as scientists, and the cycle 1 proposal deadline is coming up. It's November 24th. So as you can imagine, even with this brief description that I've given here, that as a new observatory and a large number of modes, planning the observations and developing the science cases does take some work. And that's further added to it because this is a single stream submission. So the proposal submission does include the full observation plan. So that really takes some technical work to understand what the best way to achieve your science goals here. So my bottom line advice for everyone is, if you have an intention of submitting a JWST proposal for cycle 1, get started now. But use the great ideas that we discussed over the course of this meeting to develop those science cases and be prepared to make those submissions. There are a huge number of resources that are already available from STSCI. This is one particular article that I find very useful that we published in August, which is called "How to Get Started on JWST Cycle 1 Proposals," that has further links to a number of different pieces of information. But on the STSCI website, you'll find general descriptions of a number of resources, different links that take you to more detailed descriptions, for example, of the instrumentation, or a full toolbox for proposal planning. And there are two particular features I do want to call your attention to. One is the user documentation, so-called JDocs. That is the overall documentation that you can refer to. It's not a single manual intended to be read cover to cover. It's a bit more like a wiki where you can drop in at any location and work your way around. So that means the information is very rich, but also it's non-linear, and so it will take some time to explore to really understand what's available. The other thing I want to point you to is the help desk. And if you do come up with questions, I really encourage you to submit those to the help desk for a couple of reasons. One is that for non-confidential sorts of information, then we can share not only the questions, but also the answers with everyone. That many of your questions may be also those for others. And so then that becomes a repository of knowledge for everyone. So as I said, if you do come up with questions, please use the help desk to submit them. Another place to get some information is the JWST Observer YouTube channel. So there are a number of videos available, starting with some basic overview of the different software tools that are out there, not only to be helpful, but some of which are genuinely required for the proposal submission, as well as the more detailed information about those different tools. So that's the YouTube channel. And of course, JWST Observer, that's for you as scientists, is on other social media as well, including Twitter and Facebook. So that's a place where you can find news. All right, so that's JWST coming up, very exciting, and realities soon. I do also want to talk a little bit about some further opportunities that may be coming from NASA and other agencies. And one of those coming from NASA is in the context of the US Astronomy and Astrophysics Decadal Survey that's going on right now, the so-called Astro 2020 process. So the process is ongoing. A number of different science panels have met and made some assessments of the state of the field, both in terms of scientific areas as well as state of the profession. And now that information is being combined. And it'll be some time into next year when we expect the final report from the Astro 2020 committee. One aspect of information that was fed into this assessment, though, was 4 different study teams that NASA sponsored over an extended period to really develop well thought out and advanced concepts for possible flagships to come out of this. And so there were 4 different study teams that were sponsored, coming up with ideas for an X-ray observatory called LINX, HABEX, whose main science focus is on exoplanets, a large ultraviolet optical and infrared surveyor that allows for deep studies not only of exoplanets, but also across the full range of astrophysics. And finally, something that's more pertinent here is we're looking at thermal infrared opportunities called Origins. So the great breakthrough of Origins is to deliver something that's 1,000 times more sensitive than any previous infrared mission. And so there's a very broad wavelength coverage that would be provided from about 3 to 588 microns, actively cooled, relatively large aperture with primary instrumentation that provides spectroscopy, polarimetry, and for the particular science case of transit spectroscopy, providing ultra stable opportunities for that. Just to highlight one of the science cases from Origins, a little bit biased, I admit, which is again taking us back to that case of looking at the emission from galaxies, particularly galaxies that have active nuclei and star formation in them. So here we've got our nearby friend Circinus. But the advantage of Origins then is looking at the sensitivity and wavelength coverage that it will provide that will really let these kinds of galaxies be observed out to large redshifts, still having access to those great diagnostic lines. So Origins has applicability for broad concept, the broad science cases of lots of areas of astrophysics, galaxy formation and evolution, following the trail of water, and also working at the fundamental question of, are we alone? Another concept that is being developed now is the Space Infrared Telescope for Cosmology and Astrophysics, or SPIKA. And this is now in a concept led by ESA with JAXA participation, and it remains a candidate for Cosmic Vision's M5. And so next year, there should be a decision made about that. So again, pretty broad wavelength coverage, actively cooled, 2.5 meter aperture, with several different instruments being developed for spectroscopy and imaging, including some very high spectral resolution spectroscopy and polarimetry. So just a few words about some of the complementarity between space and the ground. So space has some very obvious advantages of sensitivity and wavelength coverage provided by getting above the atmosphere, but some disadvantages of larger costs and also the long timelines to develop. As you can imagine, these concepts that we're talking about that really have taken decades to develop. And so from the ground, we've got the disadvantage of the atmosphere, but larger telescopes are feasible. And because some things are lower cost, we can develop some specialized approaches, for example, for high spectral resolution, and also have a shorter time to develop and implement some new technology, which gives us some opportunities. So I think it's on us thinking about our science cases and our science needs to really help to build some community that wants to use these different capabilities. Observers need users to ultimately produce science outcomes. That's how we identify ourselves as successful. And so that user science interest contributes to those decisions. for both space and ground, decisions about what kinds of facilities to build and what to offer. And I'll note that the capabilities on the ground can sometimes be more at risk for decommissioning, that there may be sufficient interest to build something, but if that community isn't there to continue to use it and deliver science results, then it's at risk. So as I say, that's why it's on us to build some of that community across space and ground. And while some of it is natural, it doesn't all happen by itself. For example, there are some incompatibilities between high sensitivity surveys that space-based users may want to have and what's possible from the ground. So I'll leave that as something, so work for us all to do as scientists. So I'll just close here with a bit of a summary, reminding us that JWST is practically here, bringing exciting and unique capabilities. Cycle 1 proposals need attention now if you're going to submit them. And as space agencies are developing possibilities for the future, executing any of these plans will really require strong and broad science cases that we, the community, need to develop. I will stop there and take some questions.
Thanks very much, Nancy, for a very nice talk. I saw that we have some questions on the Slack channel. The first one is by Bernard Brandl, who's asking, there seems to be an increasing tendency of the HST tag to say great science, but could also be done from the ground. On the other hand, the ESO VLT tags also reject proposals that a great observation could be better and more effectively done with HST. Is there a general policy? Do ST, SEI, and ESO discuss this jointly in the decade of ELTs and JWST?
So that's a great question, and I think the nature of the question points a bit to the answer that unfortunately no, we have not been discussing this together, and I can tell you that absolutely that kind of reaction that you've heard from the Hubble tax is what we expect from them, because one of the questions that they do ask is, does this really require Hubble? And looking to see if it could possibly be done another way, and if the answer is yes, then it's less likely to be approved. And so that same question will actually be asked for JWST. Could this be done from the ground? And so that's something important to answer. But I think Bernard raises that real question of maybe we as observatories should be talking a bit more, so that it's not just a black or white answer about feasibility, to really look at the best way to do some of these things.
Good. We have another question from Hendrik Lins. There is the JPL project NeoCam, or rather say NeoSM. Will this happen in the closer future?
I admit some of my ignorance about that particular project. So I think if it does go forward, it's a smaller scale than some of these flagships, and so would be on a more rapid timeline. Yeah, but I don't have a date, and I also don't know about some of the down selects that will happen with the competition that this project is part of.